Welcome and thank you for joining. In this session, we'll explore absolute values and radical expressions. Recall that when we square root a number, we've emphasized that we can only square root positive numbers. For example, the square root of 9 would be equal to 3, but the square root of negative 9 doesn't exist. And the rule that we have emphasized in the prior grades is that the expression or the number inside the radical or the radicand has to be positive, not a negative. However, when we determine the third root, say for example the third root of number 8 or the third root of negative 8, we do not encounter this problem because the third root of 8 is 2, the third root of negative 8 is negative 2 as well. So the problem that we have is with the square roots. And now we're wondering, is it just the square roots or does it have to do with something else? So we're going to move on to finding the fourth root of a number. For example, if we have the fourth root of number 16, then we'll say that, use a calculator to check the answer. The fourth root of 16 will be 2, and the fourth root of negative 16 will be undefined. So the calculator will give you an error. So the second root or the square root of a positive number exists, but the negative doesn't. The fourth root of a positive number exists, but the fourth root of a negative doesn't. So that has something to do with the value of the index. So the indices 2 and 4 have in common that they are even numbers. So we say that the eventh root of a number can only be calculated for positive numbers only. Now, this is very easy to kind of see and understand when we are working with numbers, but what can we do when we are eventh rooting, let's say, for example, variables, and we don't know their values? Let's say, for example, if we are square rooting x to the power of 2. So we want to make sure that when we square root a number, the answer exists and it is positive. And in this case, it doesn't really matter if x is positive or negative. The square root of x squared will be the square root of a positive because anything brought to the power of 2 will be positive. However, if we say that the answer is x, if x happened to be a negative, then we'll admit that the answer that we obtain is a negative number, and we never get a negative number out of an eventh root. And this is something that we want to discuss today, and we'll ask for help, the absolute value of a number. Now, most likely the absolute value concept is a brand new concept to you. So we're going to go down to the very definition of what absolute value is and explain everything in detail. So the absolute value of a number indicates the distance of a number from the origin. So absolute value and distance means the same thing. So what does that mean? So if we were here on the number line, here is the origin at 0. We had the numbers negative 3 and 3, then we'll say that the distance of number negative 3 from 0 would be equal to 3 units. And the way we write this, instead of distance we use absolute value, is the absolute value. For absolute value we use two very straight vertical lines, short vertical lines, of negative 3 will be positive 3. In a similar way, we'll say that the absolute value or the distance of number 3 from 0 would be equal to 3 units. So absolute value of 3 is 3. So let's play around with these two little sort of definitions that we created in here, which tell us that the absolute value of a number will make sure that the number outside will be positive. So we can think of the absolute value as a way to make every term or the value of every term from negative to positive and leaving positives as positive. So everything that comes out of an absolute value is positive. So we're going to play around with some numbers first. So we're going to say that absolute value of 4 is 4 because the distance of number 4 from the origin is 4. The distance of number 5 from the origin is 5 units. So absolute value of 5 is 5. The distance of 0 from the origin is 0. So absolute value of 0 is 0. The distance of number 17 from the origin is 17 units. So absolute value of 17 is 17. So let's look at some negative numbers. So we'll say that the distance of negative 4 from origin is 4. So absolute value of negative 4 is 4. The distance of negative 5 from the origin is 5. So the distance or absolute value of negative 5 is 5. Distance of negative 17 from the origin is 17. So absolute value of negative 17 is 17. So if you look at the numbers in the first column here, notice that the absolute value of all these positive numbers was equal to the number itself. So you had a 4 in here, the answer was 4. 5, the answer was 5, and so on. Whereas the answers for the absolute values of negative numbers was not exactly the same as the numbers inside the absolute value. And if you look closely at it, we can interpret these answers as the opposites of the numbers inside the absolute value. So the answer here is 4, which is the opposite of negative 4. The answer is 5, which is the opposite of negative 5. The answer is 17, which is the opposite of negative 17. So in conclusion, we're going to say that if we happen to have an unknown number x inside the absolute value, if x is a positive or equal to 0 number, the answer will be x itself, right? Because absolute value of positives or zeros equals the same values. However, if x were to be a negative number, like all these examples we looked at, then the answer will be the opposite of the number inside the absolute value, so the opposite of x. And the way we write it is absolute value of x equals the opposite of the number inside it. Again, providing that these numbers are negative. So we take the opposite of a negative to make sure that this entire number here will stay positive. So how are absolute values and radical expressions connected to each other? The story is, as we described before, that whenever we take out the square root of a negative number, it doesn't exist. And that's simple and easy to understand. But sometimes when we have variables inside the square root and we want to simplify it, we need to take out x, let's say square root of x squared. We need to take out x and we want to make sure that it stays positive. And to make it stay positive, we'll use the absolute value notation. So when do we have to worry about making sure that whatever comes outside the even root is positive, of a radical number is positive? Only when we have even root. When we have odd roots, we don't really mind. Either positive or a negative will actually have a value. So we'll get the value of them. So we're going to start off with these 3 very simple, straightforward examples, which are worth noting down and keeping them on the side just to remind yourself until the idea will click in, okay? So we're going to start off with the square root of x squared. So we have even root. So if we want to simplify this, if we want to take any x out of the root, it means that we need to make sure that it stays positive. So we're going to say that x squared itself will be positive for any real number x. Think about it. Positive to the power 2, positive. Negative to the power of 2, still positive. 0 to the power of 2 is going to be still equal to itself. So, therefore, we're going to say that if we were to find the square root of x squared, that would exist, because we're square rooting a positive number. So this will be positive all the time. So now, if you square root x to the power of 2, then the answer will be equal to x. Now, this is where we have to be careful. So if I square root x to the power 2, and you can understand and see how that is equal to x, because the index and the power will simplify, right? So that would be 2 over 2. So that's your m2, and that's your index n, which is down here in the denominator 2, which makes x, right? So we want to make sure that this x in here is this one here. It's positive. It's not a negative. So in other words, we're going to say that the absolute value, the square root of x squared would be x if x were to be positive or negative. But what happens if x were to be a negative number? So if x itself were a negative number, and we say that, hey, let's say x was negative 2, and we said that the square root of x squared is x, it means that we're admitting that that would be equal to exactly x, which was -2 right here. So in order to ensure that this number x that we've taken out of the radical stays positive, we'll keep it inside the absolute value. So we're going to say that the square root of x squared equals absolute value of x. And we're going to say that now that works not only for x positive, but for x negatives as well. And in the following example in here, I illustrate how we can get the answer wrong if we forget to put the absolute value. So if you have the square root of -3 squared, right? So it is very well hidden that that would be a root of 9. So that has to be 3. So if we say that the square root of -3 squared, that's x equals -3, equals x, we'll admit that that's -3, which is not true. So we have to keep that inside the absolute value. So I hope the idea is clear. We are going to look at some other examples. And remember that whenever we see examples and non-examples, the ideas will consolidate in our head. And if you find something that you learned for the first time a little bit more difficult than you expect it to be, that is because we can never learn or extend our understanding if we don't learn new things or more challenging things. We just have to learn to be patient with ourselves and try more examples similar to it or slightly different examples in order to fully understand the concept. So we'll move on to our next example. This time we have the square root of x to the power of 8. So if you look at the radicand here, is to the power of an even number. So if x is positive or negative, this number here will always be a positive. So the square root of x to the power of 8 would be the same as x to the power of 8 to power 1 over 2. I'm just trying to simplify now. And that would be equal to x to the power of 4. So now let's think about it. So x to the power of 8 is always positive, so the square root of it exists. The answer we get is x to the power of 4, and the next thing we have to think of is this has to be positive. Now think about it. Is x to the power of 4 positive for any value of x? So since the power is even, that will always be a positive number. So therefore, we're going to say that in this case, we do not need absolute value to protect this number from being a negative. So x to the 4 is positive for any real number x. So we'll continue with the next example. This time we have the fourth root of x to the power of 5. So again, we have even roots, which means that we have to watch out for or make sure that the numbers we take outside the radicals stay positive. So when we simplify radicals of this form, what we try to do is split the term up into two different exponential numbers. So we want to take out as many powers of 4 as we can because we have the index 4. So we'll write this as the fourth root of x to the power of 4 times the fourth root of x. So x to the 4 times x, still x to the power of 5. So let's simplify this. So we have fourth root of x to the power of 4. So we know that that would be the same as x to the power of 4, like this 4 here, divided by this 4 in here, which is x to the power of 1. Or you can just remember this most likely, right? So therefore, we're going to say that that would be equal to x. And then inside the fourth root, we have the fourth root of x. Now we're thinking, we took out x in here, but how do we make sure that this x that we took out is a positive number? Because a negative to the power of 4 can also be a positive. So if x were negative, then we're taking out a negative number in here. Now, we're going to say that in this case, believe it or not, and you're probably thinking that, oh, we need the absolute value. We won't need absolute value. So why is that? The reason why is because in the rest of the radical expression in here, we have the fourth root of x. And the fourth root of x won't exist if x is less than 0. So we can look at it this way. So this x that is inside the fourth root will guarantee in a way that the x that we take out in here is positive, because otherwise this wouldn't exist. So no need for absolute value, because the square root of x right here, the fourth root of x actually right here, or the eventh root of x, guarantees that x in here is positive. So this won't need the absolute value. Now let's move on to the next example. This time we have the third root of x to the power 3. Whenever you see that the index is odd, have no fear and just simplify like you would any number, because when it comes to odd roots, we can take out either positive or negative. So in this case, we're simply going to write x, because then index odd, the number, when the index is an odd number, the radicand can be any real number. Now we're going to look at example number 6a. So we are simplifying bigger expressions now. As you can see, we have even roots everywhere, and I took square roots in all the examples and the third root down here. So let's start with the first one. So we have coefficient, variable a, variable b. The index here is 2. So what that means is that if you want to simplify, we have to simplify the number 80 by breaking it down into two factors, one of them, preferably a perfect square, has to be a perfect square if possible. And we'll do the same thing with powers of 6 and powers of 7 for b. So we want the powers to be even so that they are divisible by 2. So in this case then, we're going to say that 80 will be written as root 16 times root 5. 16 times 5 equals 80. A to the 6 stays a to the 6. The index is already even. But for b to the 7th, we're going to split it up into b6 and b1. And that is because we want to take out, the factors, as many as possible. And the way we do that is by assigning an even power here. So power 6 and 1 is 7. Now, the square root of 16 will simplify, is 4. So 4 times root 5. The square root of a to the power 6, that's a to the power of 6 over 2. So that means a to the power 3. The square root of b to the power of 6, that's 6 divided by 2, the power, so that's b3. And then the square root of b. So next, we are going to look into which terms deserve or need an absolute value, make sure that they stay positive, and which ones don't. So for numbers, we don't have to worry. Now, a to the power of 3 came out of a to the power of 6. So when the power of a is odd, then if a is negative, then there is a potential for this term to represent a negative or to have a negative value. And we cannot take negative values out of here. So therefore, we're going to give a to the power 3 absolute value to make sure it stays positive. Now, b to the power 3. If b is negative, then b to the power of 3 will be a negative number, which means that we have square rooted a number and we have gotten a negative answer, which is not possible. So this has to stay positive. So while we must be thinking, oh, let's keep some absolute value in here, then the answer is not. Why? Because we already have a square root of b as a factor in here. And this b cannot sit in here if it's not positive. So this is that example that says that, okay, this term in here will guarantee that the expression or the variable will be positive. So b is only allowed to be positive because it's inside the root. So b to the power 3 doesn't get to have an absolute value. So now we have to clean up the expression a little bit. So whatever is inside radicals will go together, and whatever has no radicals will go together. So we're going to write 4 times a to the power of 3 times b to the power of 3 times the square root of 5 times b, and this would be the answer. So we can simplify this actually a little bit further. So you see that you have in here a to the power of 3. We can simplify an absolute value, which means we can reduce the expression inside the absolute value. We can take an a square out and then leave b3 as well next to it. And then to make up the power of a over 3, we're going to keep the a inside the absolute value. So this is positive. This is always positive because of the power of 2. This is positive because we kept it inside the absolute value. So this term is simplified. We reduce the absolute value. This is always positive because the b inside it protects it from being negative, and that would be the most simplified answer. So let's move to the next question. So we have the square root of 18, x to the 9, y 11, z third. So we have even index, power of 2, which means we need to break down the coefficient into two factors, one of them a perfect square, x9, y11, z3. So all of these need to be broken down into powers that are even multiples, right? So we have in here the square root of 9, square root of 2. For x to the 9, we have x to the 8, x to the power 1. Square root of y11, y10, y1. And square root of z to the power 3 is z to the power 2 times z to the power of 1. Let's simplify. So we have root of 9 equal to 3, and then root 2. X to the 8 will be x to the power of 4, and then square root of x. Y to the 10 is y to the power 5 times square root of y. And square root of z squared is z, and then square root of z. So next, we are trying to simplify. We have numbers 3, and then we have x to the 4, y to the 5, and z. So we brought together all the terms that didn't have radicals, and we'll bring together inside the same radical all the terms that have or are inside radicals. So the 2, the x, the y, and the z. So now we are thinking, do we need to put absolute values around any of the variables? So as you can see in here, we have x to the power 4. This will be always positive because the power is even. And in addition, you see that we have x inside the radical, which guarantees that x will be always a positive or zero number. Y to the power 5 has a potential of being negative if y were to be a negative number, but y cannot be negative because it's inside the radical, the eventh root or the square root. So that guarantees that y stays positive. And z that is outside is to the power of 1. So again, it has the potential of being negative if z were negative. But because we have z inside the square root, then this z will always have to be positive. And that's the reason why we need no absolute values at all in this case. So in the next example, which is our second last example, we have 98 x to the 14 y to the 9th. I encourage you to try this on your own. I'll continue with the explanation. So again, we have root of 98. Square root means that we're looking for perfect square factors. So root 49, root 2. And then x to the 14. So since the 14 is already an even power, so you leave it as root of x14. But y9 is an odd power, so we'll split it into y8 and y to the power of 1. So let's simplify now. Square root 49 is 7, root 2. Root of x to the 14 is x to the 7. Root of y to the 8 is y to the power 4. And then square root of y. So let's clean up the expression. So all the numbers outside radicals will combine together. So we have 7, we have x to the 7, we have y to the 4, and the root of 2y. Now remember that x to the 7 has an odd power, is outside the radical, which means that we need to keep it positive. So if x is negative, this can be, if x happens to be a negative, this can produce a negative number. So we need to make sure this stays positive, so we give it a pair of absolute value brackets, kind of. So we have 7x to the 7 in absolute value. We have y to the 4. Now think about it. Does y to the 4 need absolute value? Well, it doesn't for two reasons. First of all, if y is negative, this will still be a positive number because the power is even. And in addition, we have an extra protection here from the y. So the root 2 and the root of y will join each other inside the same radical. Now this would be the answer, and in a more simplified form, which means we reduce the expression inside the absolute value, we can write it as 7. We can take out x to the 6 because we know x to the 6 will always be positive, y to the 4, and then we'll add that absolute value of x at the end. So 6 plus 1, that equals 7. And this will be the answer in the most simplified form. Last example, we have the third root of 72 x to the 5y10. Notice that in here we have an index of 3. When the index is 3, we don't have to worry about making sure that the terms outside the radical stay positive. So as you can see, I saved the easiest example for last. Now remember though, and this is a tricky part of it, because we get so wrapped up in square roots and even roots, we only look for perfect square factors. We have to look at the index to determine what powers we need or what factors we need to take out. So we need to break this down into two factors, with one of them preferably being a perfect cube. And in this case, the perfect cube we can take out is 8. 8 is a perfect cube number because it's 2 to the power of 3. So that would be root of the third root of 8, the third root of 9, 8 times 9, 72. And then multiplied by the third root of x to the power 3. We want to simplify as many cubic roots as possible. So we need the power of x to be a multiple of 3. The highest that we can afford is a 3 times the third root of x squared. So you see that we keep them the same. And then for y to the power of 10, then we're going to have the third root of y to the power of 9. 9 is a multiple of 3, so they can simplify. And then we have an extra power for y, so the third root of y. So now let's clean up this expression. We have the third root of 8 is 2. The third root of x to the power of 3 is x. Then we have the third root of y to the power of 9, y to the power 3. So what are we left with? This number, third root of 9. And then we have the third root of x squared and the third root of y. So they will join each other in the same third root or same radical as 9x squared y. And this would be the final answer. No need to simplify any further. So I hope this made sense. I encourage you to continue practicing some questions from this worksheet and enjoy learning. Thank you for learning with me. Bye for now.